Cool. All right, so hopefully finishing this up in a very speedy 10 minutes. So I'm Evan Wong. I'm a mechanical engineer at Lockheed Martin. Um, I'm also in the Engineering Leadership Development Program, which pretty much means I'm a young engineer that's developing skills and like pursuing a graduate degree right now. Like to spend my time outside, so that's kind of about me. With my background, kind of like everybody else, done a lot of different things. I went to school at Carlisle School of Mines, where I got a mechanical engineering degree. I saw that as a good base to expand into different fields. I then started in the renewable energy sector. So I started with designing concrete wind turbines, which is I'm going to talk about in a little bit more detail today. And then I did some research for fuel cell applications and specifically in energy storage, using renewable energy sources to synthesize fuel that could later be burned. So that was kind of interesting. And now I jumped over to Lockheed Martin, where I work on high energy lasers out here in Seattle, Washington. So that's also very exciting work. So in taking after one of my managers, they start their presentations with a joke. So two wind turbines are sitting in a field. One asks the other, like, so what kind of music are you into? And the other one says, I'm a huge metal fan. So we got a few chuckles there. Going into concrete wind turbines. So if you're familiar with fluid dynamics, there's this term called the boundary effect, which essentially is the further you get away from a surface, the higher the wind speeds, and that applies to the Earth's surface as well. So the taller that we can make wind turbines, the more energy that they're going to capture. So the higher that you can build, the better. The problem with that is that you start to introduce a large moment in the wind turbines, which is kind of like this middle picture. The larger the moment arm, the more likely it's going to break at the base. And the way that you improve that is you make the base wider, which is kind of intuitive. The problem with making the base wider is how do you transport a tube that's 40 meters long and like 7 meters in diameter? And you can see that problem down here in the bottom left. You can't put it on a truck, so you can't like drive under bridges. You can't transport it across the country. So you end up with this manufacturing problem. The ways that we do it right now is offshore wind. They put the manufacturing site right on the coast. They load it onto boats. The boats drive it out or tow it out to sea. They install it out at sea. There's no problem. You could put it on a train, which has more flexible transportation like restraints, or you do something a little bit more risky is you put it on a truck, you drive it down the highway and hopefully get it to the final destination. So what we did in with wind tower technologies is we moved the manufacturing site. So this way we were able to increase the base of the diameter by almost double. And due to some mathematical equations with like the moment of inertia, it makes it about 6 times stronger, assuming that you're using the same materials. So all of a sudden you can build much taller wind turbines and generate a lot more electricity. So the way that we do that is on this top right side, you can kind of see some of the casts that we use. So we build these casts, ship them out to the site, construct them. On site, we pour the concrete and end up with a bunch of these shorter tubes of concrete that you can see. And then in 1 or 2 days, we bring in a huge crane and slowly stack these cones on top of each other. And this can get up to a height of like 141 meters or 141 yards roughly. And at the end, we run very large cables from the top of the tower all the way down to the base and pull it down. So it locks all the cylinders together. So it allows us to approach a common problem with like an uncommon solution. This middle picture right here is a picture of the prototype that is in the US. So that kind of proved out our design, and now I guess they have expanded into other domains. I guess I already went into a little bit of how we do it, but I guess to show a few more pictures, this on the left is them setting up the rebar for the foundation of the wind tower. So when this is finished, all of this would be underground, but I hope that creates a good image of how much rebar and labor is required to make these wind turbines, and kind of the scale with this person over here. The middle picture is an idea of like the stacking technique going on. I'd say it's a tense situation because you have all these concrete tubes, 100 feet, 100 feet in the air, and they're kind of just sitting there on gravity until you post tension it. And this image on the right is a picture looking up the wind turbine once it's completed. And you can see those large cables that are pulling everything down. And then I always like to kind of reflect on like what's next in the field. One, you can see here in the middle top that there's definitely restrictions on onshore wind turbines. So it's gonna be harder and harder to get those taller. So I think moving forward, there's gonna be a lot of offshore wind development. That's mainly taking place in Europe right now. I think the US has something like 7 offshore wind towers compared to hundreds in Europe. You can also see that the offshore wind potential is much greater. And as you can imagine, the wind coming across the ocean has much less resistance than the wind going across the land because of hills and trees and buildings. So I think that's kind of a way to go. The other one is kite energy. So this one's relatively new. There's a lot of different concepts out there, but you eliminate the structure problem out of it completely. You fly a large kite, the size of like an airplane or something like that, as high as you want, I guess, and you generate electricity from spinning propellers or flying your kites in a certain formation. And then I think one of my favorite, just because it's kind of unique, is this New Jersey median on the right, where they're trying to capture the wind generated by trucks on the highway. So they put these vertical spinning wind turbines in a concrete median and generate the electricity right next to where it's being consumed, so you don't have a transmission problem. And I think that's all I wanted to present. This is a picture of the prototype that was built. I believe it's in Iowa, of just like how tall these things are. And I open the floor to any questions if they're out there.
All right, so I see a couple questions in here. Thank you so much, Evan, for being patient and your presentation. So the first question I see in the chat is, what is the height of the tallest wind tower?
So it's offshore. I don't have a number for you. One thing with renewable energy is the metrics change constantly, so because it's such a developing field. The tallest that we built is 141 meters on land, but worldwide, the tallest one's gonna be offshore somewhere. I don't have a number for you, sorry.
Okay. The second question I saw is, why is a taller turbine better?
So the idea there is similar to flying a kite, where when you're starting to fly a kite, the wind is slower on the land, and the higher up the kite gets, the stronger the winds. And the reason is you can imagine the air being like a fluid and like dragging across the ground. And the further you get away from the ground, the higher wind speeds. And higher wind speeds means there's more energy to turn the blades and generate electricity.
Okay, great. And then I guess just quickly, one last question. How do the cost of concrete wind turbines compare to the cost of a steel turbine?
So it's an interesting one. They're a little bit more expensive. The other thing is it's completely different use of materials. So the concrete itself is less expensive than the steel turbines. However, as you saw with like all the rebar, there's a ton of manual labor that goes into bending the rebar into shape versus rolling a steel tube. So it's more expensive from a labor front, but not necessarily materials front.
Okay, well, thank you. Thank you so much.